Right now, without any sensation of movement, you are drifting through one of the largest and emptiest regions in the known universe. Not between galaxies, not between galaxy clusters. You are inside a void, a spherical cavity in the fabric of cosmic structure, roughly 2 billion light-years across. And for most of human history, nobody knew it was there. This is not a poetic metaphor, it is a measurement. In 2013, 3 astronomers named Ryan Keenan, Amy Barger and Lennox Cowie were cataloging the distribution of galaxies across billions of light-years when the numbers stopped adding up. They examined 35,000 galaxies and found that in every direction, extending outward for roughly 1 billion light-years, the density of galaxies near Earth was wrong. Not slightly off, about 20% lower than it should be. They were looking at an enormous underdense region surrounding our position in space. They called it the KBC Void, using their own initials, and the implications were anything but casual. If we live inside a region that is structurally abnormal, does every measurement we make carry a hidden bias? When we point our best instruments at distant objects to calculate how fast the universe is expanding, are we seeing a universal truth, or a locally distorted version of it? These questions strike at the foundation of modern cosmology, and the answers are still being worked out. To understand why this matters so much, it helps to step back and appreciate how the universe is actually organized. When most people picture the cosmos, they imagine a sky dense with galaxies in every direction. The reality is almost the opposite. Voids, enormous regions containing far less matter than average, occupy roughly 90% of the total volume of space. Galaxies, galaxy clusters, and the filaments connecting them account for only about 10% of that volume. But they contain almost all of the mass. The universe is not a smooth sea of evenly distributed matter. It is more like a cosmic foam, sometimes described as resembling Swiss cheese or a sponge. Enormous empty pockets are surrounded by dense walls and thread-like filaments of galaxies. At the intersections of those filaments, gravity has pulled matter into brilliant concentrated nodes, galaxy clusters, packed with millions of galaxies relatively close together. Between the nodes, the filaments stretch for hundreds of millions of light-years, and between the filaments, the voids expand quietly in near-total emptiness. This architecture is called the cosmic web, and it is the largest structure in nature. It took decades for astronomers to recognize it. For much of the 20th century, telescopes recorded beautiful images of individual galaxies and clusters, but the true three-dimensional arrangement remained invisible. The breakthrough came when scientists began measuring galaxy redshifts systematically, starting in earnest in the 1970s and 1980s. When a galaxy moves away from us, the light it emits is stretched by the expansion of space, shifting toward redder wavelengths. The more it has shifted, the farther away the galaxy is and the faster space is carrying it away from us. By measuring the redshift of thousands, then millions of galaxies, astronomers could calculate distances and build three-dimensional maps of cosmic structure. Those maps revealed the web in stunning clarity. The Sloan Digital Sky Survey, beginning in the year 2000, produced spectacular maps spanning billions of light-years. Suddenly the filaments were visible, great threads of galaxies branching and twisting like blood vessels, with dark bubbles between them reaching diameters of 500 million light-years or more. The largest single structures include the Sloan Great Wall, a filament roughly 1.5 billion light-years long. The universe had organized itself into something no one had anticipated from first principles, a vast and intricate architecture of matter and emptiness. The origin of this structure traces back to the very beginning of time, to quantum fluctuations in the first moments after the Big Bang. During a phase called inflation, the universe expanded exponentially fast for an almost incomprehensibly brief fraction of a second. During that expansion, quantum-scale variations in density were stretched from subatomic sizes to cosmic scales. Some regions ended up with slightly more matter than average, others slightly less. The differences were tiny, roughly 1 part in 100,000, but gravity amplifies even the smallest advantages. Denser regions attracted more matter, making themselves denser still. Less dense regions lost matter to their surroundings and became emptier. Over hundreds of millions of years, this process compounded relentlessly. Small clumps merged into larger clumps. Larger clumps collapsed into the first stars and galaxies. Groups of galaxies were drawn together into clusters, and clusters aligned along the paths of greatest gravitational attraction, forming the filaments. Meanwhile, the underdense regions continued to hollow out, their matter draining away toward the surrounding structure. Those underdense regions became voids. Scientists can watch the seeds of this process in the cosmic microwave background radiation, the faint afterglow of light released when the universe was just 380,000 years old. At that moment, the universe had cooled enough for protons and electrons to combine into neutral hydrogen, and radiation that had been trapped in the hot plasma suddenly streamed freely in all directions. That light has been traveling ever since, and today it reaches us as a nearly uniform glow of microwave radiation coming equally from every direction in the sky. But not perfectly uniform. Satellites have mapped tiny temperature differences across the entire sky, hot spots where the early universe was slightly denser, cold spots where it was slightly less dense. Those variations are the same quantum fluctuations that seeded everything. Scientists can take this map and run it forward in computer simulations to predict what the universe should look like today. Those simulations reliably produce a cosmic web of filaments, clusters, and voids, closely matching what is actually observed. It is one of the greatest confirmations in the history of science, a direct line connecting the quantum physics of the early universe to the large-scale structure we measure today. But the simulations have a problem. They rarely produce voids as large or as deep as the KBC Void. The KBC Void stretches roughly 1 billion light-years in every direction from our position, and it has a density deficit of about 20% compared to the cosmic average. One statistical analysis found that a void of this size and depth represents approximately a 10 sigma deviation from what standard cosmology predicts. In statistics, a 5 sigma result means less than a 1 in a million chance of being a random fluctuation. A 10 sigma deviation is so improbable that you would need to observe trillions of universe-sized volumes of space before expecting to find even one such void. And yet here we are, living inside one. The Milky Way is not at the exact center of the KBC Void. Measurements place our galaxy somewhere between 200 and 400 million light-years from the void's actual center. But given that the void extends 1 billion light-years in every direction, we are comfortably embedded within it. We sit well within the underdense region, surrounded by a low-density environment in all directions. If we were located instead in one of the dense filaments, in the kind of environment that accounts for the vast majority of galaxy mass, our measurements of the universe would look substantially different. Our cosmic neighborhood adds another layer to this picture. The Milky Way belongs to the local group, a collection of roughly 80 galaxies that includes our large neighbor Andromeda. The local group is itself part of Laniakea, a supercluster containing approximately 100,000 galaxies spread across 520 million light-years. And Laniakea, with all its galaxies and mass, sits entirely within the KBC Void. This sounds paradoxical at first. How can a supercluster exist inside an underdense region? The answer lies in how cosmic density is measured. The KBC Void is underdense compared to the cosmic average when evaluated over very large scales. But that does not mean it is perfectly empty or uniformly hollow. It contains localized concentrations of matter, including Laniakea, that are denser than their immediate surroundings. Think of the void as a large lowland basin. Within that basin, there are still hills and rocky outcrops. Laniakea is one of those features. But the basin itself is below the average elevation of the surrounding landscape. Our galaxy is also influenced by a smaller nearby void called the local void, which extends about 200 million light-years adjacent to our position. The gravitational imbalance created by these voids is significant enough to produce measurable motion. The Milky Way is moving away from the local void at roughly 600,000 miles per hour, pushed outward by the gravitational pull of denser regions beyond. When astronomers map the motions of galaxies out to distances of 250 million light-years, they detect bulk flows, large-scale, coherent streaming motions, where entire regions of space move together in the same general direction. The magnitude of these flows far exceeds what standard cosmology predicts without a large underdense region. The flows are directed outward from the underdensity towards surrounding filaments, and their velocities, reaching 400 kilometers per second or more, match almost exactly what models of the KBC Void would produce. The Cosmic Flows project has created the most detailed maps of these bulk motions to date. When researchers simulate how galaxies should move if they are inside a large underdense region surrounded by overdense shells, the predicted velocity patterns match observations with impressive accuracy. Standard cosmology without any void structure cannot reproduce these flows. Simulations based on the standard model predict that bulk motions should average below 100 kilometers per second when measured over scales of 200 million light-years. The observed flows are 4 times larger. This brings us to the heart of the problem, a discrepancy that has been grinding away at cosmology for more than a decade. Every measurement you have ever heard about the expansion rate of the universe might be telling us something different from what we assumed. The Hubble constant is the number that describes how fast the universe is expanding. It tells us how much faster a galaxy recedes from us for every unit of additional distance. For decades, it was poorly constrained, but 2 independent methods of measuring it eventually produced high-precision results, and they disagreed. The first method uses the cosmic microwave background. Scientists feed the precise temperature variations in this ancient radiation into cosmological models and calculate what the expansion rate should be today. The answer comes out to approximately 67 kilometers per second per megaparsec. A megaparsec is roughly 3.25 million light-years. This method probes the universe as it was nearly 14 billion years ago. The second method uses nearby objects with known brightness, particularly Type 1a supernovae and Cepheid variable stars. Type 1a supernovae occur when a white dwarf star accumulates enough mass to trigger a runaway nuclear explosion. Because the physics of the explosion is well understood, these events produce nearly identical peak brightness regardless of where they occur. By comparing how bright they actually are to how bright they appear from Earth, astronomers can calculate their distance precisely. Combined with redshift measurements, this gives a direct reading of the local expansion rate. That reading consistently comes out to approximately 73 kilometers per second per megaparsec. The gap between 67 and 73 is 9%. Both measurements carry error bars small enough that the disagreement is statistically significant, reaching 5 sigma, meaning less than a 1 in a million chance that random error accounts for the difference. This is the Hubble tension, and it has become one of the most discussed problems in modern cosmology. The KBC Void offers a natural explanation. When we measure the expansion rate using nearby supernovae, we are measuring within the void. The void is underdense, meaning there is less gravitational mass pulling back on the expanding space within it. At the same time, the matter concentrated in the denser filaments and walls surrounding the void exerts a net gravitational pull that draws galaxies within the void outward toward the surrounding structures. This gives galaxies inside the void an extra component of outward velocity on top of cosmological expansion. Those galaxies appear to be receding faster than they would in a typical region of the universe. The result is that our local measurements overestimate the expansion rate. We are not measuring the universe's true expansion speed. We are measuring the expansion rate inflated by the void's peculiar velocity field. When scientists model the effect of a void of the KBC's size and density deficit on local distance measurements, they find it can boost the apparent Hubble constant by approximately the right amount to account for the observed tension. The cosmic microwave background method is unaffected by the void because it probes the early universe, long before any voids existed. That measurement likely reflects the universe's global expansion rate more accurately. The implication is significant. The expansion rate we have measured locally for decades, and on which much of our understanding of cosmic history and dark energy is based, may be a locally biased number rather than a universal constant. This is not a minor correction. It has consequences for the age of the universe itself. Current estimates based on the cosmic microwave background place the age at 13.8 billion years. But if the local expansion rate of 73 kilometers per second per megaparsec reflected the true global rate, the universe would have been expanding faster throughout its entire history and would have reached its current size more quickly. The calculated age drops to roughly 12.7 billion years, about 12% younger. That might sound like a reasonable range, but it creates a serious conflict. The oldest stars in globular clusters, based on decades of careful stellar physics, appear to be approximately 13 billion years old. A universe that is only 12.7 billion years old cannot contain 13 billion-year-old stars. You cannot have objects older than the universe in which they exist. The stellar ages come from understanding how stars evolve over time. By observing which stars in a globular cluster have already reached the end of their lives, astronomers can estimate when all the stars in that cluster formed. The most massive stars burn through their fuel fastest. When you find a cluster whose most massive surviving stars are barely still alive, right at the edge of their lifetimes, you can infer when the cluster formed. The oldest clusters indicate formation about 13 billion years ago. The Gaia space mission, which measures precise distances to stars across our galaxy using parallax, has refined these measurements and confirmed the oldest clusters are indeed of that age. If the void inflates our local expansion measurements upward, then the cosmic microwave background estimate of 13.8 billion years is more accurate. The universe is old enough for the oldest stars to exist. The age problem dissolves, but the resolution requires accepting that we live in an unusual location, a concession that makes some cosmologists uncomfortable because it touches on one of the deepest assumptions embedded in the entire field. That assumption is the cosmological principle. It states that the universe is homogeneous, the same everywhere, and isotropic, the same in all directions, when viewed on sufficiently large scales. This principle is not just mathematically convenient, it is the philosophical backbone of modern cosmology. It says that no location is special. It says that observations made from Earth represent the universe in general. The cosmological principle is the scientific descendant of the Copernican revolution. Copernicus showed that Earth was not the center of the solar system. Later discoveries showed the solar system was not the center of the galaxy. Further observations showed the galaxy was not the center of anything. The cosmological principle is the ultimate extension of this logic. Not only is Earth not special, but there is no center, because every location is equivalent. The KBC Void challenges this directly. If we live inside an abnormally large underdense region, our location is unusual by definition. Voids are common throughout the universe, but supervoids of this size and depth are rare. Finding ourselves inside one raises the question of whether the cosmological principle truly holds at the scales we care about most. Some researchers calculate that the void, if it is as large and deep as measurements suggest, represents a violation of homogeneity serious enough to warrant genuine concern. Others argue the principle only strictly applies at scales somewhat larger than the void itself, perhaps at scales of a few hundred megapascs or more, and that the void falls in a borderline range. The debate is unresolved, but the mere fact of having to debate it marks a significant shift in how cosmologists think about our position in the universe. The void is also changing how physicists think about the two most mysterious ingredients in the cosmos, dark matter and dark energy. Voids are unusual environments where the balance between these components differs sharply from everywhere else. In dense regions, inside galaxy clusters, along the bright filaments of the cosmic web, gravity dominates. Mass pulls things together. Dark energy, the mysterious pressure thought to be driving the universe's accelerating expansion, is fighting against gravity but losing. Structure continues to form. Galaxy clusters hold themselves together despite the universe expanding around them. In voids, this balance is completely different. Matter is scarce. Gravity, already the weakest of the fundamental forces, barely functions. Without sufficient mass to pull things together, structure formation essentially stops. No new galaxy clusters can form. The void simply stays a void, and the dominant player becomes dark energy. Because dark energy does not clump like matter, it fills voids as readily as dense regions. In a place where matter has evacuated, dark energy is essentially unchallenged. The result is that voids expand faster than the rest of the universe. They grow like bubbles, pushing their boundaries outward while the filaments surrounding them act as containing walls, and even those walls are being slowly eroded over cosmic time. Observations have confirmed this directly. Galaxies near void edges move faster away from void centers than cosmic expansion alone would predict. The gravitational pull from the concentrated matter outside the void draws those edge galaxies outward, while the interior galaxies, including our own galaxy, are pushed toward the denser surrounding structures. The result is a characteristic velocity field that researchers have measured with increasing precision. This makes voids powerful laboratories for studying dark energy. In dense regions, separating the signal of dark energy from the noise of local gravitational dynamics is difficult. Everything is tangled together. But in voids, gravity is negligible. Galaxies move almost entirely in response to cosmic expansion and dark energy's repulsive pressure. By measuring how fast voids grow, how rapidly their edges push outward, scientists can test whether dark energy is constant or varies with time and space. The nature of dark energy remains one of the deepest unsolved problems in physics. It was discovered in 1998 through observations of distant supernovae that showed the universe's expansion is not slowing down, as gravity would demand, but accelerating. This was unexpected enough to earn a Nobel Prize. Dark energy appears to account for approximately 68% of the total energy content of the universe, but nobody knows what it is. One possibility is that dark energy is a cosmological constant, an intrinsic energy density built permanently into the structure of space, first introduced by Einstein as a term in his equations of general relativity. If dark energy is a constant, the void's expansion rate should follow predictable patterns based on known physics. Another possibility is that dark energy is a dynamic field that varies in strength across time and space. If that is true, the way voids expand should deviate from the constant predictions in measurable ways. The expansion history of voids encodes information about dark energy stretched across billions of years. Voids have been growing since early in cosmic history, and their current size and expansion rate reflect that entire history. By comparing predictions for void growth under different dark energy scenarios to what is actually observed, scientists can constrain what dark energy must be like, how much it has changed, if at all, and whether its strength differs in low-density environments. There is another class of phenomena voids can help explain. Light from the cosmic microwave background passes through the large-scale structure of the universe on its way to our telescopes. When it crosses a void, something interesting happens to its energy. The photons enter the void when it has a certain size and gravitational potential. By the time they exit on the other side, the void has expanded, dark energy has pushed the boundaries outward. The photons lose a tiny amount of energy in transit because the gravitational well they climbed out of was shallower when they exited than when they entered. The photon's energy is slightly reduced. This effect is called the integrated Sextuple effect, and it shows up as cold spots in temperature maps of the cosmic microwave background. These cold spots line up precisely with where large voids are independently observed in galaxy surveys. The alignment is not coincidence, it is physics, and it provides one of the cleanest independent confirmations that the voids we map in galaxy surveys are genuinely present, genuinely affecting the light that crosses them, and genuinely large enough to leave measurable imprints on the oldest light in the universe. One of the most striking examples of this connection involves the Eridanus subcloud, a vast undense region in the direction of the constellation Eridanus, roughly 1.8 billion light-years across, making it comparable in scale to the KBC Void. The Eridanus subcloud was not discovered by counting galaxies. It was found by noticing an anomalously cold spot in the microwave background, a region about 10 degrees across on the sky, where the temperature runs approximately 70 microkelvins cooler than average. This cold spot was identified in 2005 and immediately puzzled cosmologists because its size and temperature deficit were statistically unusual. Random fluctuations from the early universe can occasionally produce cold spots, but one this large and cold appears in only about 2% of simulated universes under standard cosmological assumptions. For years, some researchers speculated about exotic explanations, including signatures from a multiverse. A more conventional resolution emerged when galaxy surveys revealed a large undense region roughly aligned with the cold spot's position in the sky. The Sextuple effect from light crossing this void can account for roughly half the observed temperature anomaly, bringing the remaining discrepancy within the range of normal statistical fluctuation. The existence of two subclouds of comparable size within the observable universe, the KBC Void and the Eridanus subcloud, raises a question. Standard cosmology can tolerate one large subcloud as a statistical fluke. Two becomes harder to explain. 3 or 4 would begin to constitute evidence that large voids are either more common than simulations predict, or that something in our cosmological model is missing. This tension between observations and simulations has led some scientists to consider whether gravity itself might need revision on the largest cosmic scales. Einstein's general relativity, formulated in 1915, has passed every experimental test conducted over more than a century. It correctly predicts the bending of light around massive objects, the existence and properties of gravitational waves, the behavior of clocks at different gravitational potentials, and the dynamics of black holes. It is one of the most precisely tested theories in the history of physics. But if the KBC void is too large and too deep to arise naturally in simulations based on general relativity, combined with a cosmological constant and cold dark matter, the standard model of cosmology, perhaps gravity does not work exactly as Einstein described on cosmological scales. Modified gravity theories have been explored for decades as alternatives to dark energy or as modifications to dark matter models. The most prominent is modified Newtonian dynamics, or MOND, proposed in 1983 by Muddaha Mulgrim. MOND suggests that gravity behaves differently when accelerations are extremely small. At high accelerations, those experienced on Earth, in the solar system, or inside galaxies where orbital speeds are rapid, gravity follows Newton's laws and Einstein's corrections precisely. But at very small accelerations relevant for the outskirts of galaxies and cosmological scales, gravity becomes stronger than general relativity predicts. On those scales, you need less matter to produce the observed gravitational effects. In a MOND-based cosmological framework, structures form more efficiently because enhanced gravity on large scales pulls matter together more effectively. This produces richer superclusters and deeper voids. Computer simulations using modified gravity naturally generate voids as large as the KBC void without requiring unusually rare initial conditions. The statistical improbability disappears. However, MOND faces serious challenges. It struggles to reproduce the detailed temperature variations in the cosmic microwave background. It also has difficulty explaining gravitational lensing observations, where massive galaxy clusters bend light from background galaxies by amounts that require more gravitational mass than the visible matter plus any MOND enhancement can provide. These observations appear to require dark matter as a distinct component regardless of how gravity is modified. Other classes of modified gravity theories propose that gravity's behavior changes over very large distances, becoming effectively stronger in low-density regions like voids, while remaining conventional in denser environments. Testing these theories requires precise measurements of how matter moves and clusters in voids versus dense regions. If the velocity patterns of galaxies in voids deviate from general relativity's predictions in a systematic way, it could indicate modified gravity at work. Current observations are not yet precise enough to definitively resolve this, but upcoming surveys are specifically designed to test it. The pattern of expansion measurements at different distances reveals another troubling feature called the Hubble bubble. When astronomers calculate the Hubble constant using nearby objects within roughly 2 billion light-years, they consistently get higher values, around 73. When they use objects farther than 2 billion light-years, or when they rely on the cosmic microwave background, they get lower values, around 67. The boundary at roughly 2 billion light-years is suspiciously close to the estimated edge of the KBC void. This suggests that measurements taken within the void are inflated by our local environment, creating what amounts to a bubble of biased observations surrounding us. To see the universe's true expansion rate, you need to look beyond the bubble's edge. The hypothesis makes a specific, testable prediction. The measured Hubble constant should vary with distance. Nearby measurements should show the highest values. As you look farther out, approaching and eventually crossing the void's edge, the measured value should decrease toward the cosmic average. Recent observations are beginning to show exactly this trend. Studies using supernovae at various distances find that the inferred Hubble constant decreases systematically with redshift. The trend is not yet definitive. Measuring precise distances to very distant supernovae is technically challenging, but the direction matches the prediction from the void hypothesis. If the bubble is real, it presents a fundamental observational challenge. Most high-precision measurements of the local expansion rate necessarily use nearby objects, because those are the only ones we can observe in sufficient detail for the standard candle technique to work. We are effectively trapped inside the bubble, unable to step outside our local environment to directly compare our measurements against the unbiased universe. Breaking out of the bubble requires instruments capable of observing objects beyond 2 billion light-years with the same precision applied to nearby objects. The James Webb Space Telescope has already demonstrated the ability to observe distant supernovae with unprecedented clarity. Ground-based observatories with extremely large mirrors are discovering new standard candles, bright objects at cosmological distances that can be calibrated precisely. Early results from these extended-range observations suggest the expansion rate far from Earth converges toward the lower value predicted by the cosmic microwave background, consistent with the void hypothesis. One of the most powerful independent tools for confirming the void's existence and measuring its properties comes from baryon acoustic oscillations. These are frozen sound waves from the early universe that have become the most reliable standard ruler for mapping cosmic distances. In the first 380,000 years after the Big Bang, the universe was a hot, dense plasma where matter and radiation were tightly coupled. Sound waves, pressure waves driven by the interaction of matter and radiation, rippled through this plasma at roughly half the speed of light. When the universe cooled enough for electrons to bind with protons and form neutral hydrogen, the coupling between radiation and matter suddenly ended. The sound waves froze in place. The distance those waves had traveled before freezing, approximately 490 million light-years, left a permanent imprint on how matter is distributed throughout the universe. That characteristic scale shows up today in the statistical clustering of galaxies. If you count how many galaxy pairs are separated by various distances, there is a subtle but measurable excess of pairs separated by roughly 490 million light-years, the acoustic scale. Astronomers can measure this scale and use it as a cosmic ruler because the physics that set its size is extremely well understood. By comparing the apparent scale at different cosmic distances, scientists can trace how the universe has expanded over its entire history. Baryon acoustic oscillation surveys have mapped the three-dimensional distribution of galaxies across billions of light-years with extraordinary precision. When scientists analyze galaxy distributions in our local region and compare them to the acoustic scale measured in distant surveys, they find a clear deficit near Earth. The void shows up as a region where the observed clustering of galaxies differs from what distant measurements would predict. This provides independent confirmation that the void is real, and it allows researchers to quantify its depth and extent to within a few percent uncertainty. The Dark Energy Spectroscopic Instrument, which began science operations in 2021, is mapping tens of millions of galaxies with unprecedented accuracy. Within the next few years, its data will pin down the KBC Void's properties to a level that will either confirm or challenge the hypothesis that the void resolves the Hubble tension. If the void is as large and deep as current measurements suggest, the instrument should see the expansion rate shift downward as it probes distances beyond the void's edge. The Vera Rubin Observatory, with its massive wide-field telescope, will discover millions of new galaxies and trace the cosmic web in extraordinary detail, including the filaments and walls that surround the KBC Void. The Euclid Space Telescope is mapping the geometry of the universe's expansion across billions of years of cosmic history. Together, these instruments represent a new generation of precision cosmology, one specifically capable of testing whether our local environment has been distorting our understanding of the universe. There is a deeper philosophical layer to this story that is worth dwelling on. We do not just live in an unusual place, we live in an unusual time. The universe is 13.8 billion years old. For much of its early history, matter was distributed more uniformly. Voids existed but were smaller and shallower. Billions of years into the future, voids will have grown enormously, consuming surrounding filaments. We exist in a relatively narrow window of cosmic time when the web has differentiated into its most intricate and beautiful form, when structure exists on every scale from individual galaxies to superclusters, but when voids have not yet come to dominate completely. This timing may not be coincidental. The conditions necessary for complex chemistry, rocky planets, biological evolution, and intelligent life require a universe that is neither too young nor too old. Too early in cosmic history and there were not enough heavy elements, carbon, oxygen, nitrogen, iron, the building blocks of planets and biology, because stars had not yet synthesized and distributed them. Too late and star formation will have largely ceased, leaving only aging red dwarfs and the cold remnants of stellar evolution. Exist in the window when conditions are favorable for complexity, and we exist in the window when cosmology is possible. The cosmic microwave background is still detectable, distant galaxies are still visible, the expansion of the universe is still measurable. In the far future, civilizations arising in void galaxies will lack access to all of this. As dark energy drives accelerating expansion, the light from increasingly distant objects will be stretched to undetectable wavelengths. The cosmic horizon, the boundary beyond which light cannot reach us, will shrink over cosmic time. Objects currently visible will eventually fade from view. If a civilization arose in a void galaxy billions of years from now, the sky would be nearly empty except for their local group. The cosmic microwave background would be too faint and too cold to detect. There would be no visible evidence of the Big Bang, no distant galaxies to measure expansion across, no supernovae to trace acceleration. They would be cosmologically isolated, with no access to the observations that allowed us to construct the current picture of the universe. Such a civilization might conclude that they live in a static island universe surrounded by empty space, with no reason to suspect a vaster cosmos beyond their observational horizon. This scenario is sometimes called the dark future, the inevitable consequence of a universe dominated by dark energy. It is not happening yet, and it will not happen for many billions of years, but it will happen. The universe we can observe today, with its web of filaments and its measurable expansion history, is a resource that will not last forever. We happen to exist at the moment when it is still accessible. For void galaxies like our own, the isolation will only deepen over time. The Milky Way and Andromeda are predicted to merge approximately 4 billion years from now, forming a single large elliptical galaxy. That merged galaxy will be the dominant object in our local group, but the local group itself will become increasingly isolated as other nearby groups recede beyond our cosmic horizon over the following tens of billions of years. Star formation will gradually exhaust its fuel. The galaxy will dim, populated increasingly by old red stars and eventually only by the cold remnants, white dwarfs, neutron stars, and black holes. On time scales of trillions of years, even the black holes will eventually evaporate through a quantum process called Hawking radiation. The final state of the universe will be a diffuse haze of particles expanding forever into darkness. The void will have consumed everything. This long-range view changes how we think about life in the universe. If void environments are quieter and more stable than dense cluster environments, with fewer catastrophic collisions, fewer gamma-ray bursts from neighboring stars, less disruption from active galactic nuclei, they might actually be favorable for the development of life, despite seeming hostile at first glance. Life as we know it requires billions of years of relatively stable conditions. A galaxy in a void, evolving slowly and undisturbed, might offer exactly that. On the other hand, void galaxies tend to be smaller and lower in mass. They form stars more slowly, meaning fewer opportunities for planets to develop. The lower abundance of heavy elements in void galaxies means that the first planetary systems to form are gas-dominated rather than rocky. The complex chemistry that life requires, built around carbon, oxygen, nitrogen, and other elements heavier than hydrogen and helium, is scarcer in voids because fewer stellar generations have had time to manufacture and distribute it. Whether void galaxies are net favorable or net unfavorable for life remains an open question. But the fact that we are asking it at all reflects how much the KBC Void has changed the way scientists think about the relationship between cosmic environment and the emergence of complexity. If other civilizations exist in the universe, and given its vast scale, many astronomers consider this likely, some must inhabit void galaxies. Their experience of the cosmos would be profoundly different from ours. From a location deep inside a void, measuring cosmic expansion would be genuinely challenging. With few nearby galaxies to observe, building a comprehensive sample of standard candles would be difficult. The void's effect on local measurements could mislead them in the same way our void may have misled us, but potentially to a greater degree. They might develop entirely different cosmological frameworks, models that explain their observations without invoking cosmic expansion, or models that wrongly infer very different values for fundamental constants. This raises a question that cuts to the heart of scientific epistemology. Is our own cosmology affected by our void location in ways we have not yet recognized? We believe we understand the universe fairly well based on observations made from within the KBC Void. But what if there are systematic biases still unaccounted for? What if the universe beyond the void looks fundamentally different from what we measure locally? Standing back from the technical details, the KBC Void tells us something important and humbling about the nature of scientific knowledge. Every observation is conditioned by circumstances. We observe the universe from a particular location at a particular time using instruments with particular capabilities and limitations. Our theories are built on those observations, and they inherit all those limitations. The void is not a failure of science. It is science working as it should, an uncomfortable discovery, forcing a more honest accounting of what we can and cannot know from where we stand. The Hubble tension exemplifies this challenge. For years, cosmologists assumed both methods of measuring the expansion rate were accurately capturing a universal truth. Only gradually did the possibility emerge that one measurement might be systematically biased by our local environment. Even now the debate continues. The tension may resolve entirely through the void hypothesis. It may require modest modifications to the standard cosmological model. Or it may require something more fundamental, new physics, a dynamic dark energy, a revision of gravity on cosmic scales. The void has made all of these possibilities more open. Distinguishing between them will require observations extending well beyond the void's edge, coupled with theoretical models sophisticated enough to disentangle local effects from global ones. The next decade will be decisive. Deep surveys mapping galaxy distributions to distances of 3, 4, and 5 billion light-years will reveal whether the properties measured locally persist or change as instruments probe farther into space. Improvements in distance measurement, new standard candles, refined calibrations, better parallax measurements from space will reduce the uncertainties enough to demand a clear answer. Modified gravity debate will also be tested. Precise measurements of how matter moves in voids versus dense regions, how light bends around large structures, and how the growth of structure compares between environments will distinguish between general relativity and its competitors. If the KBC void is too large to arise under standard gravity, and if that conclusion holds up under scrutiny, it will force a genuine reconsideration of physics that has stood for more than a century. Perhaps the deepest question raised by all of this is what it means that we live here, inside this particular feature of cosmic structure. Are we extraordinarily unlucky, occupying one of the universe's most unusual locations? Or does our presence here tell us something important about the conditions necessary for life to arise and persist? One possibility is simply that unlikely things happen. The universe is vast. It contains an incomprehensibly large number of galaxies, voids, and possible locations for observers to arise. With enough chances, even very rare events occur somewhere. Perhaps we simply drew an unusual card in the cosmic lottery. This does not require any special status for Earth or our galaxy. It just accepts that out of countless possible locations, this one happened to be ours. A second possibility is that void environments are specifically favorable for the development of intelligent life, and that our presence in a void is therefore not a coincidence but a consequence. If life develops more readily in low collision, low radiation environments, then intelligent observers might preferentially arise in voids rather than in the crowded, catastrophe-prone filaments. From this perspective, asking why we live in a void would be like asking why we live on a planet with liquid water. The answer is that we could not exist otherwise. A third possibility is more unsettling. Perhaps our location reveals something about the large-scale structure of the universe that standard cosmology has not captured, a tendency for matter to organize in ways that create more large voids than predicted, driven by physics we do not yet understand. Distinguishing between these interpretations may eventually become possible. If we detect other civilizations and can determine their locations within the cosmic web, we will learn whether intelligent life arises uniformly throughout the cosmos or concentrates in particular environments. A sample of one tells us almost nothing. A sample of dozens or hundreds of civilizations could reveal systematic patterns. For now, the questions remain open. What we know is this: the KBC void is real, it is measurable, its effects on our observations of cosmic expansion are quantifiable, and it challenges fundamental assumptions that have uncrutted cosmology for decades. Whether it requires new physics, a modified understanding of gravity, or simply a correction factor applied to our existing measurements, the void cannot be ignored. We are tiny beings on a small planet in an ordinary galaxy, located in one of the umptust regions of an incomprehensibly vast universe. We are measuring cosmic properties from inside a hole in space 2 billion light-years wide, trying to determine universal constants from observations that our local environment distorts. Every telescope we point at the sky, every measurement of expansion, every inference about dark energy and the fate of the cosmos, all of it is filtered through this lens of emptiness. And yet we are aware of it. We have detected the void, measured its depth, mapped its boundaries, traced its effects through the motions of galaxies and the temperature of ancient light. We have recognized the bias and begun working to correct for it. We are not trapped by our position. We are slowly and painstakingly transcending it. That is the extraordinary thing about the KBC Void story. It is not a tale of cosmology being undermined. It is a tale of cosmology growing more sophisticated. The void pushes researchers to develop better models, make more careful measurements, and think more deeply about what can and cannot be known from a single vantage point embedded within the system being observed. It pushes science toward greater honesty about the limits of knowledge and greater ingenuity in overcoming them. The journey to understand our place in the universe continues. One measurement at a time, one correction at a time, one survey at a time. The void surrounds us, but we are learning to see past it, and what we are finding about the universe, about the nature of observation, and about the challenges of knowing anything at all from inside the system you are trying to understand, makes the effort genuinely worthwhile. If this kind of rigorous, curious exploration of the cosmos interests you, consider following along as these questions continue to be explored. The next generation of instruments is already producing data, and the answers, when they come, are likely to reshape how we understand the universe we live in. To fully appreciate what the KBC void means, it helps to understand how astronomers build maps of something as vast as the observable universe, and how long it took for the true structure of the cosmos to reveal itself. For most of the 20th century, mapping the universe was essentially a two-dimensional problem. Telescopes captured images of the sky and astronomers counted and catalogued the galaxies they saw. Early surveys produced beautiful catalogues with millions of entries, but they showed only the angular positions of galaxies on the sky. Without distance information, the three-dimensional arrangement was invisible. All those galaxies, separated by hundreds of millions of light-years in depth, appeared projected onto a flat picture. The realization that distances could be measured using Rorschach transformed the field. When a source of light moves away from an observer, the waves of light are stretched out, shifted toward the red end of the spectrum. The faster the source recedes, the more its light is shifted. Hubble showed in the 1920s that galaxies are receding from us, and that the speed of recession is proportional to distance. This relationship, now called the Hubble law, provided the key tool for depth measurement. Measure a galaxy's redshift, and you can infer how far away it is, assuming you know the expansion history of the universe. The first large redshift surveys began in the 1970s. The Harvard Center for Astrophysics survey, led by Margaret Jolk, John Huckrow and colleagues, mapped thousands of galaxies over more than a decade of painstaking work. In 1986, a preliminary visualization of the data produced one of the most startling images in the history of astronomy. The galaxies were not distributed uniformly. They were arranged in thin, arching filaments surrounding enormous dark regions, the first clear view of the cosmic web from within. Jolk and Huckrow called one particularly striking filament the Great Wall, a sheet of galaxies stretching 300 million light-years across the sky. It was the largest known structure at the time, and its existence challenged the assumption that the universe became homogeneous on scales much smaller than that. The Great Wall was later surpassed by even larger structures, including the Sloan Great Wall discovered in 2003, which spans roughly 1.4 billion light-years. These discoveries changed the questions cosmologists were asking. Instead of asking how galaxies were distributed, they began asking why the distribution had this particular character, these specific scales, these specific densities, this precise balance between filaments and voids. The answer pointed back to the physics of the early universe, to inflation, and to the quantum seeds from which all large-scale structure grew. Inflation is arguably the most consequential idea in modern cosmology, and it connects directly to why voids like the KBC exist at all. In the first fraction of a second after the Big Bang, far less than 1/1,000,000,000 of a trillionth of a second, a quantum field caused the universe to expand exponentially fast, doubling in size an enormous number of times in an almost inconceivably brief interval. During this expansion, quantum fluctuations, the inherent uncertainties built into the nature of matter and energy at the smallest scales, were stretched from subatomic dimensions to cosmic scales. Before inflation, these fluctuations were just quantum noise, the irreducible fuzziness of reality at the Planck scale. After inflation stretched them, they became slight variations in the density of matter and energy spread across regions that would eventually grow into superclusters, voids, and filaments. The pattern of fluctuations carries detailed information about the physics of inflation, what kind of quantum field drove it, how long it lasted, and what energy scale it occurred at. The cosmic microwave background preserves a snapshot of these fluctuations when the universe was about 380,000 years old. The temperature map of the microwave background is essentially an image of the seeds of all cosmic structure, the original slight density variations that gravity later amplified into everything we see today. The remarkable success of this picture is that detailed cosmological simulations, starting from the microwave background temperature map and running forward in time under the laws of physics as we understand them, produce a cosmic web that closely matches what is observed in galaxy surveys. The match is not perfect. The KBC Void is one of the places where the observed structure appears more extreme than simulations typically produce, but the overall agreement is extraordinary. Understanding where the simulations and observations agree and where they diverge is one of the most productive frontiers in cosmology today. The KBC Void sits squarely in the region of disagreement, which is precisely why it is scientifically important. To quantify how unusual the KBC Void is, researchers use statistical tools borrowed from probability theory. They run large numbers of cosmological simulations, each starting from slightly different random initial conditions, consistent with what the microwave background tells us about the early universe. They then search those simulated universes for voids of comparable size and depth to the KBC Void. The fraction of simulated universes that contain such a void gives a measure of its statistical rarity. Early analyses found the KBC Void to be roughly a 5 to 10 sigma outlier, far rarer than anything that should plausibly occur by chance in our observable universe under standard cosmological assumptions. Later analyses, using more realistic treatments of how void boundaries are defined and measured, found somewhat lower but still significant tension. The exact sigma level depends on the analysis method, but the conclusion is consistent across approaches. The KBC Void is substantially larger and deeper than standard simulations typically produce. Some researchers have challenged these claims, arguing that the void's properties have been overestimated due to observational biases or analysis choices. Detecting underdense regions in 3 dimensions requires careful corrections for selection effects, the fact that surveys are not perfectly uniform in their coverage, and that fainter galaxies are easier to detect in nearer regions. These selection effects can create apparent uncondensatas that are partly instrumental rather than real. Careful analyses accounting for these effects still find a significant uncondensata, though the estimated depth has been revised somewhat compared to early measurements. The debate over the void's exact properties illustrates a general challenge in observational cosmology. The universe cannot be measured perfectly. Every survey has gaps in sky coverage, redshift completeness, and brightness sensitivity. Every measurement of galaxy density depends on assumptions about how many galaxies of each type exist and how they are distributed. Extracting the underlying true density requires modeling these observational effects accurately, and different modeling choices can produce different answers. This is not a failure of the scientific process. It is the scientific process, the iterative refinement of measurements and models as more data become available and analysis techniques improve. The upcoming generation of surveys will provide dramatically better data, and the uncertainties around the void's properties will shrink substantially. One important piece of evidence that supports the void's reality comes from an entirely different direction: the thermal Sunov-Zuldovich effect. When the cosmic microwave background photons pass through hot gas, the kind found in galaxy clusters, electrons in the gas scatter the photons and boost their energy slightly. This creates a distinctive signature, a slight increase in microwave background temperature toward the frequency where the boost is most prominent. By mapping this signature across the sky, astronomers can independently locate galaxy clusters and measure their gas content. Surveys using this effect reveal the distribution of massive galaxy clusters across large portions of the sky. When these cluster maps are overlaid on galaxy Rudolph surveys, they consistently show that the region corresponding to the KBC Void contains fewer massive clusters than comparable regions of sky. The deficit of clusters is independent evidence, from a completely different observational technique, that the KBC Void region is genuinely underdense. Further support comes from lensing surveys. Massive structures in the universe bend light from background galaxies through a process called gravitational lensing. Dense regions produce stronger lensing signals. Underdense regions produce weaker signals. By mapping the statistical pattern of lensing across large areas of sky and comparing it to the expected signal from a universe with and without a large void, researchers can independently test the void's presence. Current weak lensing surveys show a deficiency in the lensing signal in the direction and at the redshift corresponding to the KBC Void, consistent with the galaxy count and velocity field evidence. The convergence of multiple independent lines of evidence, galaxy number counts, peculiar velocity flows, baryon acoustic oscillation scales, microwave background cold spots, cluster distributions, and weak gravitational lensing, makes a compelling case that the KBC Void is real and that it is having a measurable effect on our observations. The question is no longer primarily whether the void exists. The question is precisely how large and deep it is, and exactly how much it affects the measurements that form the foundation of modern cosmology. Precision matters enormously here, because the Hubble tension is itself a precise discrepancy. The local measurement of 73 km per second per megapasuk and the global measurement of 67 km per second per megapasuk disagree by 9%. The void needs to be capable of producing a bias of at least that magnitude in local expansion measurements to fully explain the tension. Early calculations suggested that a void of the KBC's estimated size and density deficit could produce a bias of roughly 5 to 10%, which brackets the observed discrepancy nicely. But those calculations depend on the void's depth and extent, both of which remain uncertain at roughly the 20% level. If refined measurements find the void is somewhat shallower or smaller than current best estimates, the void hypothesis may explain only part of the Hubble tension, leaving the remainder to be accounted for by other effects or by genuine new physics. If measurements confirm the void is as extreme as currently estimated, the void hypothesis may fully resolve the tension without requiring any modifications to fundamental physics. Either outcome would be scientifically important. There is also a related question about the peculiar velocity of our own galaxy. The Milky Way is moving at roughly 600 km per second relative to the rest frame of the cosmic microwave background, a motion inferred from the slight temperature asymmetry in the microwave background between the direction we are moving toward and the direction we are moving away from. This large-scale motion has a component pointing away from the local void and toward denser structures in the direction of what astronomers call the Great Attractor, a concentration of mass beyond the Hydra-Centaurus supercluster. Mapping the sources of this motion is the goal of the Cosmic Flows project and related efforts. By combining data from thousands of galaxies measured with distance indicator methods, including Type 1a supernovae, Cepheids, the Tully-Fusher relation for spiral galaxies, and the fundamental plane for elliptical galaxies, researchers construct three-dimensional velocity maps that reveal the gravitational landscape of our cosmic neighborhood. These maps show that our galaxy is simultaneously being pushed away from nearby voids and pulled toward distant dense concentrations. The KBC Void contributes a measurable component to our peculiar velocity. The more precisely this velocity is measured and modeled, the better researchers can isolate the void's contribution and constrain its properties. An interesting implication of our motion is that the Milky Way is not falling deeper into the void, we are being accelerated out of it. The galaxies of the local group are moving at hundreds of kilometers per second toward the filaments surrounding the void. This motion has been ongoing for billions of years and will continue into the future. Eventually, on timescales far beyond the current age of the universe, the Milky Way and its merged companion Andromeda will have moved substantially toward the void's edge, though the expansion of space will counteract this motion on the largest scales. The distinction between peculiar velocity and cosmological expansion is crucial for understanding what the void means. Cosmological expansion carries all galaxies apart from one another regardless of their positions. It is a property of space itself rather than of galaxy motions. Peculiar velocities are additional motions on top of expansion, driven by local gravitational forces. Within the void, dark energy dominates and the void itself expands, but individual galaxies within it also have peculiar velocities driven by the density gradient between the void and its surroundings. Separating these two components, expansion and peculiar velocity, is one of the central technical challenges in modern observational cosmology. It requires measuring galaxy distances and rudeshafts with high precision across large volumes and applying statistical techniques to extract the underlying velocity field. The void's presence makes this separation more complex and more important than it would be in a uniform universe. The next major advance in this area will come from peculiar velocity surveys using gravitational wave sources. When two neutron stars or a neutron star and a black hole spiral together and merge, they produce both gravitational waves and a burst of light, a color nova. The gravitational wave signal provides a direct measurement of the distance to the merger, independent of any assumptions about stellar physics or calibration ladders. The light signal provides the rudshaft. Combining these gives the peculiar velocity directly and independently of all traditional distance indicators. The LIGO and Virgo gravitational wave detectors have already detected dozens of neutron star mergers, though most are too distant for precise peculiar velocity measurements with current sensitivity. Next-generation gravitational wave observatories will be dramatically more sensitive. Detecting mergers at cosmological distances with enough precision to independently measure the Hubble constant and map peculiar velocity flows. If the void is responsible for the Hubble tension, these measurements should reveal a consistent expansion rate that converges with the cosmic microwave background value once averaged over volumes large enough to extend beyond the void. There is one more remarkable dimension to the KBC Void story that connects it to the history of ideas about our place in the cosmos. Throughout the development of modern science, each major advance has progressively displaced humanity from any position of special significance. The Copernican revolution removed Earth from the center of the solar system. The galactocentric picture placed our solar system on the periphery of a typical spiral galaxy rather than at its center. The expansion of the universe in the early 20th century removed any concept of a fixed center of space. The cosmological principle declared that all locations in the universe are equivalent. Each step made our position seem less special, more typical, more interchangeable with any other point in the vast cosmos. The void complicates this trajectory. We find ourselves in a genuinely unusual location, not at the center of anything, but in a large, improbable, underdense region. If the cosmological principle holds strictly, such a region should barely exist anywhere in the observable universe, but we are here, measuring it from within. Some scientists find this troubling. It suggests that our observations may not represent the universe in general, that our cosmological models, calibrated to measurements made from within the void, carry a systematic bias that we are still working to understand and correct. Others find it instructive rather than troubling. The fact that we can detect the bias, quantify it, and begin correcting for it is a testament to how powerful modern observational and theoretical tools have become. The void does not invalidate the cosmological principle, it tests it. And in testing it, it forces cosmologists to engage more carefully with the question of what scale the principle actually applies at, and what level of homogeneity the universe actually achieves on different scales. These are not new questions, but the KBC Void gives them new urgency. Related to this is the question of what other large-scale anomalies might exist in the observable universe and what they collectively tell us. The cold spot in the microwave background associated with the Eridanus supervoid is one example. The alignment of the largest temperature fluctuations in the microwave background, the so-called axis of evil, is another anomaly that some researchers have proposed may reflect large-scale inhomogeneity. The possibility of a hemispherical asymmetry in the power of microwave background fluctuations is a third. Most of these anomalies are individually explicable as statistical flukes at the level of a few % probability. But when taken together, some researchers argue they may reflect an underlying pattern of inhomogeneity at scales comparable to or larger than the observable universe. Others caution that combining multiple marginal anomalies does not straightforwardly multiply the significance of any individual one, and that the history of cosmology is littered with apparent anomalies that dissolved under more careful analysis. The KBC Void stands out in this landscape because it is well supported by multiple independent observational lines rather than resting on a single statistical comparison. It is real in a way that some of the other proposed anomalies may not be. And it is large enough, at roughly 1% of the diameter of the observable universe, to have a genuinely measurable effect on cosmological observables, making it not merely an academic curiosity, but a practical correction that must be applied to precision cosmological measurements. On the question of dark energy, the void may ultimately provide some of the cleanest tests available. As noted earlier, dark energy dominates in void environments where gravity is weak. The way voids expand and evolve over cosmic time is a sensitive probe of dark energy's nature. If dark energy is a cosmological constant, perfectly uniform throughout space and time, then void expansion rates should follow a specific, well-defined trajectory. If dark energy is a dynamic field, different regions of the universe may expand at slightly different rates depending on local conditions. Some theories of dynamic dark energy, called quintessence models, predict that the field's strength can vary across space. In regions where the field is slightly stronger, expansion would be slightly faster. In regions where it is weaker, expansion would be slower. Voids are the places where any such spatial variation would be most easily detected because the signal from dark energy is cleanest there. If quintessence is real and spatially varying, precision measurements of void expansion rates at different cosmic distances and in different directions could reveal the variation. This prospect makes the KBC Void not just an embarrassing anomaly that needs to be explained away, but a potential scientific instrument, a natural laboratory sitting in our cosmic backyard, uniquely suited to answering one of the deepest questions in physics. Understanding what dark energy is will not come from a single measurement or a single discovery. It will come from the accumulation of many independent lines of evidence, each providing a slightly different probe of how space expands, how structures form, and how the balance between gravity and dark energy changes over cosmic time. The KBC Void contributes to several of these lines simultaneously. It affects peculiar velocity measurements, it influences the apparent Hubble constant, it creates a clean environment for dark energy observations, and it provides a test case for structure formation models. As measurements continue to improve, the picture of our cosmic environment will sharpen. The properties of the void will be pinned down to better precision. The contribution of the void to the Hubble tension will be quantified more precisely. The modified gravity hypothesis will be tested more rigorously. And the question of whether the void is truly anomalous under standard cosmology, or merely at the tail of a distribution that standard cosmology can accommodate, will approach a definitive answer. Whatever the final answer turns out to be, the journey has already produced significant scientific value. The discovery of the KBC Void forced a re-examination of assumptions that had been taken for granted for decades. It generated new theoretical frameworks for understanding how local environments bias cosmological measurements. It spurred new observational programs specifically designed to map the universe at distances beyond the void. And it reminded the entire field that science is conducted from inside the system being studied, that observers are embedded in a universe they can never view from the outside, and that this embeddedness carries real consequences for what can be known and how. The void surrounds us, 2 billion light-years of relative emptiness in every direction, punctuated by sparse galaxies drifting through the quiet. The nearest dense filament of the cosmic web lies hundreds of millions of light-years away. Beyond the void, the universe continues, denser, more structured, full of the galaxy clusters and bright intersecting filaments that we thought we were measuring all along. We know the void is here now. We are measuring it, mapping it, correcting for it. Instruments currently operating are collecting the data that will resolve the Hubble tension within the next decade. New telescopes are being built that will map the structure of the cosmos with a precision that previous generations of astronomers could not have imagined. The universe will be measured not just from within the void, but from beyond it, from vantage points distant enough to see the void from the outside and compare those distant views against what we measure from within. When that comparison is complete, we will have a clearer picture of what the universe actually looks like when viewed without the lens of our unusual cosmic neighborhood. Whether that picture confirms everything we currently believe, or forces revisions to one or more of our most fundamental models, the knowledge gained will represent a genuine advance, earned through the patient application of curiosity, ingenuity, and the determined refusal to let observational accidents masquerade as cosmic truths. We live inside a cosmic hole 2 billion light-years wide. We know it, we are learning from it, and in learning from it, we are becoming more capable of understanding the universe that contains it. To appreciate the scale of what we are talking about, it helps to build up from the familiar. Start with Earth, a rocky sphere roughly 12,700 kilometers across. Light takes about 42 milliseconds to travel around it. The Moon orbits at a distance of roughly 384,000 kilometers, which light crosses in about 1.25 seconds. The Sun is 150 million kilometers away, 8 minutes and 20 seconds at the speed of light. The nearest star system, Alpha Centauri, is 4.2 light-years away. The entire Milky Way galaxy, a flattened disk of 200 to 400 billion stars, stretches roughly 100,000 light-years across. The Andromeda galaxy, our nearest large galactic neighbor, sits 2.5 million light-years away, so far that the light arriving at your eyes tonight left before modern humans existed. The local group, our gravitationally bound collection of roughly 80 galaxies, spans about 10 million light-years. Laniakea, the supercluster that contains the local group, stretches 520 million light-years and contains 100,000 galaxies with a total mass equivalent to roughly 100 million billion times the mass of our Sun. And Laniakea, with all of its 100,000 galaxies and all of its incomprehensible mass, sits inside the KBC Void. The void itself extends roughly 1 billion light-years in every direction from somewhere near our position. Its volume is approximately 4.2 billion cubic light-years. To have an intuitive sense of this number, consider that the entire local group, those 80 galaxies, fits inside a sphere 10 million light-years across. The KBC Void is 100 times wider than that, and its volume is 1 million times larger. The void is not just large. It is operating on a scale that dwarfs everything familiar in astronomy except the universe itself. Most of that vast volume contains almost nothing by astronomical standards. The void has roughly 15% of the average cosmic density of galaxies. If a typical region of space with the same volume contains 10,000 galaxies, the same volume in the KBC Void contains roughly 1,500. The remaining 8,500 galaxies are somewhere else, concentrated in the filaments and walls surrounding the void, in the cosmic web's bright highways of matter. The void galaxies that do exist within this emptiness are distributed unevenly. Some small clusters and groups persist, as Laniakea demonstrates, but between these concentrations, the void is genuinely sparse. A hypothetical civilization on a planet in a typical void galaxy, not in a cluster or group, just a lone dwarf galaxy drifting through the void, would look out at a sky almost completely devoid of other galaxies. Their Milky Way equivalent would shine brilliantly. Their local cluster, if they had one, might be visible. But the great structures of the cosmic web, the rich filaments, the massive superclusters, would be hundreds of millions of light-years away, visible only as faint smudges barely distinguishable from the cosmic background. The concept of dark matter is inseparable from understanding voids. Dark matter is a form of matter that does not emit, absorb, or reflect light in any known way, but which reveals its presence through gravity. It accounts for roughly 27% of the universe's total energy mass content. Ordinary matter, everything made of atoms, including all the stars, planets, gas, and dust that we can see, accounts for only about 5%. Dark energy comprises the remaining 68%. Dark matter was first inferred in the 1930s, when Fritz Zwicky measured the velocities of galaxies in the Coma cluster and found they were moving too fast to be held together by the visible matter alone. Whatever was binding the cluster had to be far more massive than the luminous material. Vera Rubin and Kent Ford's observations in the 1970s showed that stars in spiral galaxies orbit at speeds that should cause the outer regions of galaxies to fly apart, unless there is far more mass present than the visible stars and gas. That unseen mass is dark matter. Today, dark matter is understood as the gravitational scaffolding on which all visible structure is built. In the early universe, dark matter density fluctuations grew first under gravity, forming massive halos into which ordinary matter, hydrogen and helium gas, subsequently fell. Stars and galaxies formed inside those halos. The cosmic web of filaments and voids that characterizes the large-scale universe today reflects the distribution of dark matter halos at different sizes and masses. Within voids, dark matter is present but at lower density, roughly 15% of the cosmic average, matching the density of luminous galaxies. This makes voids the regions where dark matter is most dilute, its gravitational influence weakest, and dark energy's relative importance greatest. Mapping dark matter in and around voids using gravitational lensing provides direct information about how dark matter halos form and cluster in low-density environments, which complements information from the dense environments where most galaxy surveys concentrate. The interplay between dark matter, dark energy, and ordinary matter is what determines whether the KBC void can form under standard cosmological assumptions. In the standard lambda cold dark matter model, where lambda refers to the cosmological constant representing dark energy, and cold dark matter refers to slow-moving dark matter particles, structure formation follows a well-defined statistical pattern. Initial density fluctuations grow at a rate determined by the balance between gravity pulling matter together and cosmic expansion pulling it apart. The resulting distribution of structures, how many galaxies, clusters, filaments, and voids of each size exist, is a prediction of the model. The fact that the KBC void is larger and deeper than simulations typically produce suggests either that the model has underestimated the rate of structure growth, that the initial fluctuations in our observable universe were unusually large in this region, or that some effect beyond the standard model is at work. Each of these possibilities has different implications. If structure growth is faster than standard predictions, it could indicate that dark matter is not as cold as assumed, that it has some residual thermal velocity that affects how it clumps. Warm dark matter models, where dark matter particles have higher velocities than in the cold dark matter case, predict slightly different structure formation rates. However, the KBC void is so large that warm dark matter corrections alone are unlikely to explain it. If the initial fluctuations were simply unusually large in our region, this is statistically possible but increasingly improbable as the void's estimated size increases. A 10 sigma fluctuation is not absolutely impossible. In an infinite universe, every possible fluctuation occurs somewhere. But finding ourselves in such a region, and finding that other large structures like the Eridanus supervoid may also be more extreme than average, suggests this explanation may be insufficient. The modified gravity possibility remains on the table precisely because it offers a systematic explanation rather than a statistical one. Under modified gravity, large voids are not rare anomalies. They are natural outcomes of structure formation when gravity behaves differently at low acceleration scales. If future measurements confirm that the KBC void is indeed as extreme as current estimates suggest, the modified gravity explanation will deserve serious consideration, even given its other challenges. One specific modified gravity framework that has received attention is the theory of emergent gravity, proposed by Eric Verland in 2016. Verland argues that gravity is not a fundamental force but an entropic phenomenon, an emergent consequence of the distribution of information in the universe. In his framework, dark matter is not a separate particle species, but an apparent effect arising from the way gravity emerges from quantum information. The theory predicts specific deviations from general relativity at low accelerations that could be relevant for void formation and evolution. Emergent gravity and similar approaches are highly controversial and lack detailed observational confirmation. They are mentioned here not as established physics, but as illustrations of how the anomalies associated with the KBC Void have motivated genuinely novel theoretical ideas. When observations persistently challenge standard models, the scientific response is to explore alternatives, even unconventional ones, and see which survive contact with data. The observational program to test these ideas is multi-pronged and involves instruments on the ground, in orbit, and under construction. Each brings different strengths and probes different aspects of the problem. The Vera Rubin Observatory, located in northern Chile, began science operations recently. Its primary instrument is the Legacy Survey of Space and Time, a 10-year survey that will image the visible sky repeatedly, capturing images in 6 wavelength bands every few nights. The survey will detect tens of billions of astronomical objects and measure the shapes of hundreds of millions of galaxies with sufficient precision to map weak gravitational lensing across an enormous volume. This will produce the most detailed 3-dimensional map of the distribution of dark matter in the universe ever created, extending well beyond the KBC Void's edge. The Euclid Space Telescope, operated by the European Space Agency, is specifically designed to map dark energy's effects on the universe's expansion and structure growth over billions of years of cosmic history. It will survey roughly 1/3 of the entire sky, measuring the shapes and redshifts of hundreds of millions of galaxies out to redshifts corresponding to times when the universe was less than half its current age. Euclid will measure the baryon acoustic oscillation scale at many different cosmic epochs, tracing how the expansion rate has changed over time and distinguishing between different dark energy models. The Nancy Grace Roman Space Telescope, operated by NASA, will complement Euclid with deep observations of smaller sky regions, observing galaxy shapes and supernovae with high resolution. Its wide field of view and infrared sensitivity make it particularly powerful for observing galaxies at high redshift, where cosmological effects are strongest. The Square Kilometre Array, a massive radio telescope being constructed across Australia and South Africa, will conduct the largest survey of neutral hydrogen ever undertaken. Because neutral hydrogen traces gas in and around galaxies, including void galaxies that retain large gas reservoirs, the SCAR will provide a complementary picture of matter distribution across cosmic scales, including within the KBC Void. Its sensitivity will detect hydrogen in galaxies far fainter and more distant than current radio surveys can reach. Together, these instruments represent an investment of billions of dollars and decades of scientific effort aimed at understanding the fundamental physics of the universe, and the KBC Void sits squarely in the scientific questions they are designed to address. Within the next decade, data from these surveys will either confirm that the void explains the Hubble tension, reveal that new physics is needed, or produce some combination that reshapes cosmology in ways currently difficult to predict. The history of cosmology is full of moments when a persistent anomaly turned out to be the leading edge of a fundamental discovery. The anomalous precession of Mercury's orbit, unexplained by Newtonian gravity, was eventually accounted for by Einstein's general relativity, and in the process revealed the true nature of gravity. The apparent constancy of the speed of light in early interferometry experiments, which seemed to contradict classical physics, led to special relativity and the unification of space and time. The discovery in the 1990s that distant supernovae were fainter than expected, which should have been a mere calibration puzzle, turned out to be evidence for the accelerating expansion of the universe and the existence of dark energy. The Hubble tension and the KBC Void may represent the next such moment, or they may resolve into a correction factor applied to existing models without requiring fundamental revision. Either outcome will advance understanding, the willingness to take observational anomalies seriously, to investigate them rigorously rather than dismissing them as measurement errors, and to follow the evidence wherever it leads. These are the practices that have driven every major advance in the history of cosmology. The void is not the end of the story. It is a chapter within a much longer investigation, one that began when Galileo first pointed a telescope at the sky, that took a major turn when Hubble discovered the universe was expanding, that deepened when astronomers found the expansion was accelerating, and that continues today with instruments capable of measuring the universe's structure and evolution with a precision that would have seemed like science fiction to earlier generations. Every generation of astronomers has believed they were close to a complete picture of the cosmos, and every generation has been surprised by what the next level of precision revealed. The cosmic web was not anticipated. Dark energy was not anticipated. The Hubble tension was not anticipated. The KBC Void and all that it implies about our position in the universe and about the reliability of our measurements was not anticipated. Whatever comes next, it is unlikely to be anticipated either. The universe has a long history of surprising us, and the void, this enormous, empty, measurement-distorting hole in the cosmic web that we have been living inside all along without knowing it, is a reminder that the cosmos is strange, vast, and not finished with its revelations. We are void dwellers, we are cosmologists. We are against all probability, aware of the space we inhabit and capable of mapping it, measuring it, and slowly, patiently understanding it. That remains one of the most improbable and astonishing facts in the known universe. One dimension of the void story that deserves more attention is what it reveals about the nature of voids themselves, not just the KBC void in particular, but the general class of structures that dominate the volume of the universe. Voids are the universe's most abundant feature and also its least studied. For decades, most observational attention focused on the luminous, high-density regions where galaxies cluster together. The voids were simply the spaces between the interesting stuff. That perception has changed substantially over the past 2 decades. Voids turn out to be scientifically interesting precisely because of what they lack. In a void, the processes that dominate galaxy evolution in dense environments are absent. There are no major mergers between large galaxies, because large galaxies are rare and widely separated. There is no stripping of gas from galaxies by intracluster medium, because there is no dense cluster gas. There is no triggering of star formation by tidal interactions, because neighboring galaxies are too far away to exert significant tidal forces. Galaxies in voids evolve in relative isolation, driven primarily by their own internal physics. This makes void galaxies natural laboratories for studying the intrinsic properties of galaxies, what galaxies do when left to themselves, without the constant interference of their environment. Compare a void galaxy to a cluster galaxy of similar mass, and the differences reflect the accumulated effect of environmental interactions over billions of years. This comparison is one of the most powerful tools available for understanding what shapes galaxy properties. The observations consistently show that void galaxies are bluer in color than their cluster counterparts of similar mass, meaning they have higher current rates of star formation relative to their stellar mass. They have more irregular morphologies, less of the smooth, rounded shapes that result from mergers settling galaxies into symmetric configurations. They tend to be more gas-rich, retaining reservoirs of neutral hydrogen that cluster galaxies have had stripped away or converted into stars. Some void galaxies show particularly unusual properties. A class called void spiral galaxies includes some of the most pristine spiral structures known, galaxies with remarkably regular, undisturbed disk profiles and long, sweeping spiral arms, unscarred by the mergers and interactions that have reshaped most cluster galaxies. These pristine spirals offer a view of what galaxies look like when structure forms purely from internal gravitational dynamics, without environmental disruption. The metallicity, the abundance of elements heavier than hydrogen and helium, is systematically lower in void galaxies. Heavy elements are produced inside stars through nuclear fusion and distributed through the interstellar medium when those stars die. In galaxies with higher star formation rates over longer histories, successive generations of stars have progressively enriched the interstellar medium. Void galaxies with their lower star formation histories have had less time and fewer stellar generations to build up their heavy element content. The lower metallicity affects what kinds of planets can form and what kinds of chemistry can occur. Rocky, Earth-like planets require silicon, iron, oxygen, and other elements produced by earlier stellar generations. In the earliest void galaxies, these elements would have been scarcer, potentially reducing the likelihood of Earth-like planetary systems compared to galaxies in denser, more evolved regions. The question of how galaxy properties vary with environment is not unique to voids. It is a central question in galaxy evolution research. But the void environment provides the cleanest test case because it is the most extreme case of low density and isolation. Understanding how galaxies behave in voids helps calibrate models of environmental effects across the entire spectrum of cosmic environments, from the extreme isolation of voids to the extreme density of cluster cores. One of the most intriguing recent results in void galaxy research involves what are called extremely isolated galaxies, objects with no significant neighbor within distances of several million light-years. Some of these objects, catalogued in surveys like the KIG Karashentseva Isolated Galaxy and SIG Catalogue of Isolated Galaxies, surveys reside deep within voids and have evolved for billions of years without interaction. Their properties encode information about what galaxies do when environmental influences are minimized to the greatest possible degree. These isolated galaxies tend to have lower surface brightness than galaxies in denser environments. They are more diffuse, with their stars spread out over larger areas. This is consistent with the expectation that without mergers and tidal interactions to compact them, galaxies expand and flatten over time. Their rotation curves, profiles of how fast stars orbit at different distances from the galaxy center, are unusually regular, without the distortions caused by tidal interactions or recent mergers. Some surveys have found that extremely isolated galaxies have lower supermassive black hole masses relative to their total stellar mass than cluster galaxies. In the standard picture, supermassive black holes grow primarily when two galaxies merge. The collision disrupts the distribution of gas in both galaxies, funneling material toward the galactic centers where it feeds the black holes. Without mergers, black hole growth is suppressed. The comparatively underdeveloped black holes in isolated void galaxies support this picture and provide constraints on models of black hole growth and feedback. The feedback from active galactic nuclei, the powerful energetic outflows produced when a supermassive black hole is actively accreting material, plays an important role in regulating star formation in galaxies. When the black hole feeds, it releases enormous energy that can heat and expel the surrounding gas, temporarily shutting off star formation. This feedback mechanism is thought to explain why massive galaxies stop forming stars at some point in their histories. In void galaxies with less active black holes, this feedback may be weaker, potentially allowing star formation to continue at low levels for longer than in cluster galaxies. The slow, steady star formation histories of many void galaxies are consistent with this suppressed feedback scenario. The cosmic web also plays a role in determining how gas reaches galaxies in the first place. In standard models of galaxy formation, gas flows from the cosmic web into galaxies along cosmic filaments, the same structures that contain the concentrated galaxy populations. This accretion of fresh gas sustains star formation over long periods. Galaxies in filaments have access to this supply of fresh material from the surrounding cosmic web. Galaxies in voids are more isolated from filamentary gas supplies, which may contribute to their overall lower rates of star formation. But there is a complication. Some simulations suggest that void galaxies may actually accrete gas more smoothly and continuously than cluster galaxies, which experience violent mergers and the disruption of their gas supply by cluster processes. The smooth, continuous accretion in voids allows a steady trickle of fresh gas to maintain star formation over very long timescales without the peaks and valleys that characterize star formation in denser environments. This could explain why some void galaxies have surprisingly blue colors, not because they are forming stars rapidly, but because they are forming stars continuously and have not yet exhausted their gas supply. The relationship between the void environment and the properties of the galaxies within it connects to one of the most debated topics in modern astrophysics, the question of nature versus nurture in galaxy evolution. How much of what a galaxy looks like today is determined by its initial conditions, the mass of the dark matter halo it formed in, the properties of the gas that originally collapsed, versus how much is determined by what happened to it afterward in its environment? The void galaxy population provides a partial answer. By studying galaxies in voids where environmental influences are minimized, researchers can isolate the intrinsic contribution to galaxy properties. Comparing void galaxies to cluster galaxies of similar masses, then reveals how much the cluster environment has modified their properties. The result is that environment matters enormously. Cluster galaxies and void galaxies of similar mass look dramatically different, but initial conditions also matter, setting the baseline properties that environment then modifies. This is relevant not just for understanding galaxies in the abstract, but for understanding our own galaxy. The Milky Way sits within the KBC Void, though as part of the Laniakea supercluster it is not in the most isolated part of the void. It has experienced the interplay between its void location and its membership in a supercluster, and its properties, its size, its current star formation rate, its chemical composition, its central black hole mass, reflect that history. The Milky Way is a fairly typical large spiral galaxy, which might seem at odds with being in an unusual void, but the void's effect on galaxy properties is subtle and cumulative. Our galaxy's properties are within the range of what standard cosmological models predict for galaxies of its mass, with perhaps some features that could be attributed to our relatively low-density environment. The modest star formation rate of the Milky Way, currently producing roughly a few solar masses worth of new stars per year, is consistent with a galaxy that has been forming stars steadily for 10 billion years without the disruption of major mergers, which is the kind of history you would expect for a galaxy in a relatively underdense environment. Understanding the connection between our void environment and our galaxy's properties is part of the broader effort to understand our cosmic context. And our cosmic context, as the KBC Void illustrates, has consequences far beyond the properties of our own galaxy. It affects how we measure the universe, what cosmological parameters we infer, and how confident we can be in the picture of the cosmos we have constructed. Consider what it took to even become aware of the void. It required the development of redshift surveys capable of mapping the three-dimensional distribution of tens of thousands of galaxies across billions of light years. It required sophisticated statistical techniques to compare the observed galaxy counts to theoretical predictions. It required models of cosmic structure formation detailed enough to calculate what galaxy density should be as a function of position. And it required the willingness of researchers like Keenan, Barger, and Cowie to take the discrepancy seriously rather than attributing it to measurement error. This chain of capabilities, telescopes, spectrographs, computing power, statistical methods, theoretical models, scientific culture, represents centuries of accumulated effort. Galileo built a telescope in the early 17th century. Hubble measured galaxy distances in the 1920s. Penzias and Wilson detected the cosmic microwave background in the 1960s. Geller and Huckra mapped the Great Wall in the 1980s. The Sloan Digital Sky Survey revealed the cosmic web in detail, starting in the early 2000s. Each step built on the previous ones, each generation of instruments and ideas making possible the next discovery. The KBC Void was always there, a billion light-year-wide feature of the universe that we have been sitting inside for the entirety of human existence, for the entirety of Earth's history, for longer than the Sun has existed. But we did not know it until 2013. That is a remarkable fact about the pace of cosmological discovery. The single most consequential feature of our local cosmic environment, the feature that may be distorting every measurement we make of the expanding universe, was unknown until the 21st century. It prompts the question, what are we still missing? What other features of our cosmic environment remain undetected because we lack the instruments, the surveys, the statistical methods, or the theoretical frameworks to recognize them? The history of astronomy strongly suggests the answer is quite a lot. Every time a new capability has been developed, a new wavelength band opened up, a new survey completed, a new theoretical insight applied, previously invisible features of the universe have come into view. Radio astronomy revealed quasars and pulsars and the cosmic microwave background. X-ray observations revealed the hot gas filling galaxy clusters. Infrared surveys revealed the dust-obscured star formation in distant galaxies. Gravitational wave detectors revealed the merging of compact objects across cosmic distances. Each new window onto the universe has exposed phenomena that were completely unknown beforehand. The next generation of observatories will open new windows. Gravitational wave astronomy with next-generation detectors will map merging black holes and neutron stars across billions of light years. Neutrino telescopes will detect particles from the most energetic cosmic explosions. Space-based infrared observatories will peer into the earliest epochs of galaxy formation when the universe was less than 1 billion years old. Each of these new capabilities carries the potential for revelations comparable to the discovery of the cosmic web or the KBC Void, features of the universe that are obvious in retrospect, but completely invisible beforehand. This is the nature of scientific progress in cosmology. It is not a smooth march from ignorance to knowledge, but a series of discontinuous revelations, each requiring new tools and new ideas. The KBC Void is one of those revelations. Its full implications are still being worked out. Its role in cosmology is still being established, but its existence is secure, and the questions it raises are real. We stand inside a cosmic hole 2 billion light-years across, peering out at a universe whose properties we have been measuring through a distorting lens of relative emptiness. We now know the lens is there. We are learning to account for it. The measurement of the universe continues, more carefully and more honestly than before. That is how science works, not through the absence of error, but through the recognition of error and the determination to correct it. Not through perfect knowledge, but through the endless refinement of imperfect knowledge. Not through certainty, but through the disciplined pursuit of understanding in the face of complexity and uncertainty. The KBC Void did not undermine cosmology. It made cosmology more rigorous. It will continue to do so as observations improve, as theories are tested, and as the universe, patient, vast, and indifferent to our confusion, continues to reveal itself one measurement at a time. There is a thread running through all of this that connects the very large to the very small, from the 2 billion light-year void down to the quantum fluctuations that seeded it. One of the most profound insights in modern physics is that the structure of the universe on the largest scales was determined by quantum physics operating on the smallest scales in the earliest moments of time. The voids and filaments and clusters we see today are the amplified shadows of quantum randomness from before the universe was a second old. Quantum mechanics is the framework governing the behavior of matter and energy at the atomic and subatomic scale. At its heart is a principle of irreducible uncertainty, the Heisenberg uncertainty principle, which states that certain pairs of physical properties cannot both be precisely determined at the same time. Position and momentum are one such pair, energy and time are another. This uncertainty is not a limitation of our measuring instruments, it is a fundamental feature of reality. During inflation, the energy field driving the exponential expansion of the universe was subject to quantum uncertainty. Slight random fluctuations in the field's energy were unavoidable. These fluctuations were tiny, variations of about 1 part in 100,000, but they were real, physically meaningful variations in the density of energy filling the early universe. And because inflation stretched every region of space by an enormous factor, these quantum-scale fluctuations were amplified to cosmological scales. The regions of slightly higher energy density eventually became slightly denser in matter, and those density differences were the seeds from which all cosmic structure grew. The specific statistical properties of the initial fluctuations, how the amplitude of the fluctuations varies with their spatial scale, carry information about the inflation process. By measuring the detailed pattern of temperature fluctuations in the cosmic microwave background, cosmologists can infer the properties of the inflatoned field, constrain models of inflation, and test whether the standard inflationary picture is correct. The statistical pattern of the microwave background fluctuations is expected to be Gaussian, meaning that the fluctuations at different positions are random and independent, following a bell curve distribution of amplitudes. Simple single-field inflation models predict Gaussian fluctuations to very high precision. Non-Gaussianity, departures from the Gaussian prediction, would indicate either more complex inflation models or novel physics in the early universe. Current measurements find the fluctuations to be Gaussian at the level of precision achievable with existing instruments. This is a strong constraint on inflation models, ruling out many multi-field and non-standard inflationary scenarios. But it also means the initial conditions for structure formation were governed by pure statistical chance. Every region had a random chance of being slightly overdense or underdense, with no preferred location and no systematic favoritism toward particular scales. From this statistical starting point, the specific realization of the universe we inhabit, including the presence of the KBC void in our particular location, emerged through the operation of gravity over billions of years on a random set of initial conditions. The void is not arbitrary in the sense that its formation is understood physically. But its presence in our specific location, at this specific size and depth, was determined by the particular random draw of quantum fluctuations in our patch of the universe during the first fraction of a second of its existence. This is a remarkable convergence. The largest structure in our local cosmic environment, spanning 2 billion light-years and potentially biasing all of our measurements of the universe, was ultimately determined by quantum randomness operating on scales smaller than an atom in the first moments after the Big Bang. Physics operates across 60 orders of magnitude of scale, and the consequences of its operation ripple through all of them. The connection between quantum mechanics and cosmic structure is one of the most tested predictions in all of physics, and it works with extraordinary precision. The pattern of fluctuations in the microwave background, predicted from inflationary quantum mechanics and subsequently confirmed by satellite observations, matches theoretical predictions at the level of a few parts in 100,000. This is a more precise confirmation of theoretical predictions than almost any other measurement in science. Yet the statistical nature of the prediction means that specific local realizations, like the presence of the KBC void, can deviate from the statistical mean. In a large universe, deviations many sigma away from the mean occur somewhere. The question is whether our specific realization is so extreme that it challenges the inflationary framework itself, or whether it is simply an unusual but not impossible draw from the predicted distribution. This is the core tension in the KBC void debate. Standard cosmology based on inflation and cold dark matter predicts a specific statistical distribution of void sizes and depths. The KBC void appears to fall in the extreme tail of that distribution, possibly beyond what any realization of the model should produce in a universe the size of ours. If confirmed at high significance, this would be evidence against the standard model, not just an unusual fluctuation within it. Resolving this tension requires improving both the measurement of the void's properties and the theoretical predictions against which those measurements are compared. On the theoretical side, cosmological simulations have become dramatically more powerful in recent years. Modern simulations track billions of dark matter particles and millions of gas cells across volumes comparable to the observable universe, following the formation of galaxies, clusters, and voids from the initial quantum fluctuations to the present day. Simulations like the Illustris TNG project, the Eagle simulation, and the Horizon AGN simulation follow galaxy formation in detail, accounting for the effects of supernova feedback, black hole accretion, stellar winds, and radiation on the distribution of gas in and around galaxies. These simulations can be used to predict not just the statistical distribution of void sizes, but also the properties of galaxies within voids, the velocity fields around voids, and the observable signatures that distinguish voids of different depths and sizes. The challenge is that even the most detailed simulations cannot run at the resolution needed to track individual galaxy formation processes across volumes of several billion light-years. There is always a trade-off between volume and resolution. Large volume simulations sacrifice resolution to cover enough space to sample the distribution of rare structures like supervoids. High-resolution simulations cover smaller volumes and miss rare large-scale structures. Statistical comparisons between observations and simulations must therefore account for finite volume effects. The fact that a simulation covering a cubic volume, 1 billion light-years on a side, may not contain any example of the KBC void, not because the void is impossible, but because the simulated volume is too small to sample it adequately. To make statistically valid comparisons, researchers use many smaller simulations and build up the expected distribution of rare events through theory, combined with ensemble averaging. As computing power continues to increase, simulations will grow both larger in volume and higher in resolution, reducing the uncertainty in statistical comparisons. The next decade of cosmological simulations will make it possible to say with much greater confidence whether the KBC void is truly anomalous under standard cosmology or whether it falls within the predicted distribution, given the volume of the universe we can observe. Understanding the void also requires understanding the broader landscape of anomalies in the observed universe. The KBC Void is not the only feature that has challenged standard cosmological predictions. The Bullet Cluster, two galaxy clusters caught in the aftermath of a collision, shows dark matter and ordinary matter separated in a way that strongly supports the existence of dark matter, but poses challenges for modified gravity theories. The distribution of satellite galaxies around the Milky Way shows them aligned in a planar structure, which conflicts with the expectation from standard simulations that satellites should be distributed approximately isotropically around their host. The missing baryon problem, the observation that the amount of ordinary matter in observed galaxies and clusters is less than the total ordinary matter predicted to exist by cosmological models, has been partially resolved by observations of the warm-hot intergalactic medium, the diffuse gas between galaxies. The S8 tension is a discrepancy between the amplitude of matter density fluctuations measured from the microwave background versus from weak gravitational lensing surveys, somewhat analogous to the Hubble tension. Each of these discrepancies may have individual explanations within the standard model, or they may collectively be pointing towards something systematically wrong with the model. The history of physics suggests that when multiple independent anomalies point in similar directions, it is worth taking seriously the possibility that they reflect a common underlying cause. Whether the various cosmological tensions share a common explanation, perhaps related to the large-scale structure of the universe, perhaps related to modified gravity, perhaps related to novel dark matter or dark energy physics, is one of the most actively investigated questions in contemporary cosmology. The KBC Void contributes to this conversation not just as one anomaly among several, but as the anomaly with the most direct observational consequences. Because the void affects how we measure the expansion rate of the universe, the most fundamental cosmological observable, understanding it is prerequisite to resolving the Hubble tension, which in turn affects inferences about dark energy, the age of the universe, and the completeness of the standard cosmological model. We are at an interesting moment in the history of cosmology. The standard lambda cold dark matter model has been extraordinarily successful, passing test after test over 3 decades, but cracks have appeared. The Hubble tension, the S8 tension, the anomalously large KBC void, the puzzling alignment of microwave background multiples, these may all be statistical flukes, but the accumulation of marginal anomalies is beginning to attract serious attention. The resolution, whatever form it takes, will require the kind of high-precision data that the next generation of surveys is being built to produce. It will require theoretical work sophisticated enough to make precise predictions and identify which observations most sensitively distinguish between competing models. And it will require the scientific community's willingness to question assumptions that have served well for decades if the evidence demands it. The KBC Void is, in a sense, a gift, an enormous, nearby feature of the universe whose observational consequences are clear and whose implications for fundamental physics are profound. It is a signpost pointing toward questions that matter. And it is the kind of discovery that reminds us, in the most concrete possible terms, that we are not passive observers of an abstract universe, but participants embedded within it, shaped by it, measuring it from inside it, and gradually, painstakingly, learning to see past the limitations our position imposes. 2 billion light-years of emptiness surrounds us, and from within that emptiness, we have learned to map the cosmos, measure its expansion, trace its history back to the first moments of time, and recognize the ways our own location distorts our view. That is an extraordinary achievement, built across generations of human curiosity and scientific effort. The void is not the end of our understanding, it is an invitation to deepen it. Before leaving the subject of the KBC Void, it is worth pausing on one more dimension, what it means to make cosmological measurements at all, and why the void represents such a fundamental challenge to that enterprise. Science works by comparing observations to predictions. A theory makes a prediction about what should be observed under certain conditions. An experiment or observation tests whether that prediction holds. If it does, confidence in the theory increases. If it does not, the theory must be revised or replaced. For this process to work, the conditions under which the observation is made must be understood. In a laboratory on Earth, this is relatively straightforward. The controlled environment is designed specifically to isolate the phenomenon of interest from confounding factors. But in cosmology, there is no possibility of controlled experiments. The universe is the laboratory, and the observer is stuck inside it. Cosmologists cope with this by assuming, wherever possible, that their vantage point is representative, that the piece of the universe they can observe reflects the properties of the whole. The cosmological principle codifies this assumption. It says that the universe is statistically the same everywhere, so measurements from any particular location can be treated as measurements of universal properties. The KBC void is a direct challenge to this assumption for measurements made within the void. Any measurement that is sensitive to the local matter density and expansion rate measurements using nearby standard candles are exactly that will be biased by the void in a predictable but imperfectly known way. The bias cannot be removed without knowing the void's properties precisely, and the void's properties cannot be determined perfectly with current data. This is the epistemological core of the problem. It is not that cosmologists made errors. It is that the universe has placed them in a location where perfectly rigorous measurements of local conditions give biased estimates of global properties. Recognizing this bias, quantifying it, and correcting for it is a task that will occupy cosmologists for the next several decades. The correction is possible in principle because the bias is not random. It has a specific, predictable signature. It affects expansion rate measurements, peculiar velocity measurements, and the apparent density of galaxies within a specific volume around our position. By modeling all of these effects consistently, researchers can separate the local void signature from the underlying global cosmological signal. This is analogous to a problem that occurs in any measurement where the instrument is embedded in the quantity being measured. A thermometer immersed in a fluid changes the temperature of the fluid slightly by its presence. To measure the fluid's true temperature, you must account for the thermometer's effect. A cosmologist measuring the universe's expansion rate from within a void must account for the void's effect. The physics is more complex, but the principle is the same. What makes the cosmological case challenging is the scale and the precision required. The void is 1 billion light-years across, and the correction needed to account for its effect on the Hubble constant is about 9%, comparable to the current measurement uncertainties, but systematically affecting all local measurements in the same direction. To distinguish the void's effect from other possible explanations for the Hubble tension, measurements must be made at multiple distances and with multiple independent techniques, all cross-checked against each other. This is exactly what the current and next-generation surveys are designed to do. By measuring the expansion rate at distances ranging from tens of millions to several billion light-years, using methods including standard candles, standard rulers, and gravitational wave sources, cosmologists will build up a comprehensive picture of how the apparent expansion rate changes with distance and direction. That picture will either confirm the void hypothesis or rule it out, directing attention toward whatever alternative explanation the data requires. The outcome of this investigation will matter far beyond the specific question of the Hubble tension. If the void fully explains the tension, it will confirm that the standard cosmological model is correct, and that precision cosmology can be done successfully from within an unusual local environment, provided that environment is properly characterized. If the void only partially explains the tension, new physics will be needed, and the search for that physics will reshape theoretical cosmology. If the void turns out to be less extreme than current estimates suggest, the Hubble tension will remain unexplained, and the pressure on standard models will intensify. In any of these outcomes, the scientific community will be wiser. The process of investigating the void, building better surveys, developing more sophisticated analysis methods, constructing more detailed theoretical models, will leave a permanent legacy of improved observational and theoretical tools, regardless of what the data ultimately show. This is, in microcosm, how science always works. The question that gets asked is not always the most important question. Often it is a specific, concrete problem. Why do these two measurements disagree? That turns out to require, for its resolution, advances in understanding that end up being more valuable than the original question. The investigation of the Hubble tension through the lens of the KBC void is reshaping how cosmologists think about local biases, structure formation, galaxy evolution, and the nature of dark energy. Those advances will persist and build on each other long after the specific question of whether the void resolves the Hubble tension has been settled. The universe is under no obligation to be simple, or to reveal its secrets at a scale we can manage comfortably. The KBC Void is a feature of the cosmos 2 billion light-years in extent, and understanding its effects requires mapping the universe across 3, 4, and 5 billion light-years with precision measurements. That is a genuinely hard problem. It requires the best instruments humanity has built, operated by the most skilled observers in the most sophisticated theoretical framework ever developed. We are doing this, right now. Telescopes on mountain summits in Chile and Hawaii are collecting light from galaxies at the edge of the void and beyond. Space telescopes are mapping the shapes of hundreds of millions of galaxies with nanometer-level precision. Computing clusters are running simulations of volumes bigger than the observable universe. Theorists are developing new frameworks for understanding how large-scale structure biases local observations. The void is large, but we are not small in the relevant sense. We are small in scale, but not in capability. We have built tools that extend our reach across billions of light-years, and our sight back billions of years. We have developed methods that let us measure properties of the universe to 1 part in 10,000. We have constructed theories that connect quantum fluctuations in the first nanoseconds of time to the arrangement of galaxies 10 billion light-years away. And we have discovered, through the application of all of these tools, that we live inside a cosmic hole 2 billion light-years wide, and we know it, and we are learning from it. That knowledge, earned through generations of scientific effort, carried in the minds of researchers working at the intersection of theory and observation, transmitted through papers and conferences and collaborations across continents, that knowledge is one of the most remarkable things our species has ever produced. The void surrounds us, but we have learned to see it, and in seeing it we see farther.